This section examines the operation of the drum brake. Drum brakes were once common on all wheels of light vehicles. But on modern designs, they are usually found on just the rear wheels, in disc drum combinations. The drum brake has two brake shoes with a friction material called a lining attached. These shoes expand against the inside surface of a brake drum and slow the wheel down. The harder the linings are forced against the brake drum, the higher the braking force that is applied. They can be expanded mechanically or hydraulically. The main advantage claimed for drum brakes is that the shoe mountings can be designed to assist their own operation. This is called self-energizing. Less hydraulic pressure is then needed to stop the vehicle, which is why many older drum-braked vehicles didn't use a brake booster. The main disadvantage of drum brakes is that the friction area is almost entirely covered by lining, so most heat must be conducted through the drum to reach the outside air to cool. With hard use, this can cause overheating and eventually brake fade. Brake fade is the gradual loss of brake stopping power during prolonged or strenuous use. Very high temperatures occur at the brake drum, and that causes a deterioration in the frictional value of the lining or pad material. It's common in drum brakes. Another problem with drum brakes is that it is difficult to get water out of the drum. If a vehicle is driven through water, it takes longer to get the brakes working effectively. Three brake designs are in general use: single leading shoe, twin leading shoe, and duo servo. Each one uses the wedging or self-energizing action of the brake shoe to assist the lining to grip the rotating drum when the brakes are applied. The twin leading shoe has an actuator for each brake shoe. The actuator can be mechanical. However, a hydraulic actuator is popular on light vehicles. The hydraulic actuator is called the wheel cylinder. This arrangement has two wheel cylinders with one piston in each cylinder. When the brakes are applied, hydraulic pressure forces each piston to move outwards, pushing on one end of the brake shoe. The direction of rotation of the drum produces a wedging action on both brake shoes, so they are both called leading shoes. This system was once popular on front wheels because it is very efficient in the forward direction. This is due to the self-energizing or self-wedging action of the shoes as the drum rotates. Its main disadvantage is that it is only about 30% as efficient in reverse, so it is usually combined with a single leading shoe arrangement on the rear to provide a balanced system. The single leading shoe system uses a single wheel cylinder with two pistons. When the brakes are applied, both shoes press against the brake drum. One shoe is called leading shoe, the other is called trailing. The leading shoe tends to be self-energized, while the trailing shoe tends to be forced off the drum. This arrangement is common on rear wheels as they work equally well in forward and reverse, so it makes an effective handbrake. They can also have a self-adjusting mechanism. The duo servo design also uses one wheel cylinder with two pistons. It is a high energy brake, that is, it exerts large self-energizing forces. The lower ends of the shoes are linked but aren't firmly anchored to the backing plate. This lets the complete shoe assembly float within limits. When the brakes are applied, both shoes are carried around by the drum until the secondary shoe contacts the anchor pin. The self-energizing force of the primary shoe and its wheel cylinder application force is now transferred to the secondary shoe through the lower linkage. Force is then being applied to the secondary shoe from both ends. the wheel cylinder at the top, and the linkage from the primary shoe at the bottom. The primary shoe has the shorter lining and is always fitted ahead of the wheel cylinder in terms of drum rotation. It's most important that the shoes are fitted correctly, since it's the secondary shoe that does most of the work. The linings may also have different frictional values. The colours of the retraction springs indicate different spring strengths. This design is common on rear wheels and it works well in both directions. Drum brake systems need to be adjusted to allow for wear of the lining. If they are not adjusted, pedal travel will be too long to be safe. This section examines divided systems for drum brakes. Modern drum braking systems use a tandem master cylinder to provide divided or dual line braking. A divided system is safer in the event of partial failure. Fluid loss in one half of the system still leaves the other half able to halt the vehicle, although with an increase in stopping distance. A wheel's braking ability depends on the load it's carrying during braking. A front-engined rear-wheel drive car has around 40% of its load on its rear wheels, so its braking system can be divided in a vertical or front-rear split. This puts the front wheels in a different system from the rear wheels. If one half of the system fails, the front or the back, there's still enough separate braking capability left in the other half to stop the vehicle. This section looks at the brake pedal. The brake pedal uses leverage to transfer the effort from the driver's foot to the master cylinder. Different lever designs can alter the effort the driver needs to make. It is usually suspended from a bracket between the dash panel and the firewall. In many vehicles, the brake pedal is either connected to a switch or in contact with one. It operates the stoplights when the brake pedal is depressed.
A lever is basically a bar which is pivoted at some point called a fulcrum. An effort applied at some point on the lever overcomes a load at some point also on the lever. There are three basic types of lever: lever of the first order, lever of the second order, lever of the third order. They each have their own applications. The ratio of load and effort is called mechanical advantage. Using the right kind of lever in the right way allows a user to lift larger loads with smaller efforts.
This section looks at the master cylinder. The master cylinder is connected to the brake pedal via a push rod. This is a single master cylinder for a drum brake system. Its one piston has a primary and a secondary cup. These are also known as seals, because when force is applied to the brake pedal, the primary cup seals the pressure in the cylinder. The secondary cup prevents loss of fluid past the end of the piston. An outlet port links the cylinder to the brake lines. An inlet port connects the reservoir with the space around the piston. A compensating port connects the reservoir to the cylinder ahead of the primary cup. With the brakes off, this port connects the brake system with the reservoir. It compensates for changes in volume of the fluid due to heat or wear. The rod from the brake pedal pushes on the piston. It moves, closing off the compensating port and trapping fluid ahead of the primary cup. Any fluid trapped in the cylinder is then forced through a valve called a residual pressure valve into the brake lines. When the brakes are released, the master cylinder piston returns to its original position. When the piston fully returns against its stop, the primary cup uncovers the compensating port. Fluid ahead of the primary cup can now return this way to the reservoir. When the pedal is released quickly, the spring makes the piston return quickly, but the fluid cannot return as quickly to the cylinder. A low pressure area develops ahead of the primary cup, which could draw air into the system. To prevent this, small holes are drilled in the piston. Fluid from the reservoir can pass through the inlet port and past the edge of the primary cup. This is called recuperation. When the fluid in the lines returns to rest, its pressure is held above atmospheric pressure by a valve called the residual line pressure valve. The residual pressure helps stop air from entering at the wheel cylinder, and it keeps fluid from leaking out. With a basic master cylinder in the braking system, any loss of fluid, say because a component fails, could mean the whole braking system fails. To reduce this risk, modern vehicles must have at least 2 separate hydraulic systems. That's why the tandem master cylinder was introduced. Like 2 single piston cylinders end to end, a tandem cylinder has a primary piston and a secondary piston. Each section of the cylinder has inlet and outlet ports and compensating ports. There can be 2 separate reservoirs, or just one, but it is divided into separate sections. When the brake is applied, the primary piston moves and closes its compensating port. Fluid pressure rises and acts on the secondary piston. It moves, closing its compensating port. Pressure builds up in this circuit. Both pistons then move and displace fluid into their separate circuits and apply the brakes. If there is a failure in the secondary circuit, the primary system continues to operate normally, but with increased travel. If the primary circuit fails, no pressure is generated to move the secondary piston. So a rod attached to the front of the primary piston will push the secondary piston directly so that it still operates. A switch can warn of loss of pressure in the front or rear circuits, or one that warns of low fluid level can be fitted to the reservoir. The tandem master cylinder, just like the single piston master cylinder, can have problems with the low pressure area developing when the piston returns quickly but the fluid lags. The tandem master cylinder overcomes this by using grooves in the side of the primary cup. These grooves allow fluid to flow from the inlet port into the low pressure area. This section examines the power booster. A power booster or power brake unit uses a vacuum to multiply the driver's pedal effort and apply that to the master cylinder. This increases the pressures available from the master cylinder. Units on petrol engines use the vacuum produced in the intake manifold. Vehicles with diesel engines cannot use manifold vacuum, so they are fitted with an engine-driven vacuum pump. The most common booster now operates between the brake and master cylinder. It increases the force that acts on the master cylinder. Whenever the pedal is depressed, the power brake unit assists the driver. The level of assistance depends on the pressure applied. When the driver moves the brake pedal pushrod, it transmits movement through the power unit to the master cylinder piston to apply the brakes. It also operates a control valve that admits air at atmospheric pressure to the rear of the unit. How it works depends on the position of the pushrod. A hose connects the intake manifold to a vacuum check valve on the power unit. With the engine running, the vacuum in the intake manifold is used to evacuate the power unit. This valve is held off its seat and a vacuum is produced in both chambers of the unit. The chambers are separated by a flexible rubber diaphragm attached to the diaphragm plate. It is held in the off position by a diaphragm return spring. The master cylinder pushrod and the control valve assembly are centrally located on each side of the plate. As the brakes are applied, the pedal pushrod and plunger move forward in the diaphragm plate. This brings the control valve into contact with the vacuum port seat. It closes the vacuum port, sealing off the passage connecting the chambers. Further movement of the pushrod and plunger moves the air valve away from the control valve to open the atmospheric port. Air at atmospheric pressure comes into the air filter and passages and enters the chamber at the rear of the diaphragm. The difference in pressure now on both sides of the diaphragm moves the diaphragm plate forward, and it takes the master cylinder pushrod with it. Hydraulic pressure builds up in the brake system to operate the brakes. As pressure rises, a counterforce acts through the master cylinder pushrod and the reaction disc. This counterforce acts against the plunger and pedal pushrod. It tends to move the plunger slightly to the rear, and it closes off the atmospheric port. If the vacuum source is interrupted, then as the pedal is pushed down, the pedal pushrod and plunger assembly come in contact with the reaction disc. This forces the master cylinder pushrod forward to operate the brakes. The pedal force needed then is much greater than with vacuum assistance. During application, the reaction force against the valve plunger works against the driver to close the atmospheric port. With both the atmospheric and the vacuum ports closed, the power unit is in a holding position. It stays this way until increased pedal force reopens the atmospheric port, or a drop in pedal force reopens the vacuum port. With the force on the pedal held constant, the valve returns to the holding position. But if the pedal is fully applied, the plunger moves away from the control valve to open the atmospheric port and give full power application. When the brakes are released, vacuum returns to both sides of the diaphragm, so the spring releases the brakes. When the engine is switched off or stops for any reason, no vacuum is available. The vacuum remaining in the booster, held by the non-return valve, will provide for at least one power-boosted application. After this, the brakes will still operate, but without power assistance, they require more effort from the driver. This section looks at the emergency brake for a drum brake system. All vehicles must be fitted with at least 2 independent systems. They were once called the service brake and emergency brake. Now they are usually referred to as the foot brake and the park brake. Most light vehicles use a foot brake that operates through a hydraulic system on all wheels, and a hand-operated brake that acts mechanically on the rear wheels only. One common use of the handbrake system is to hold the vehicle when it is parked. The systems are designed to be independent so that if one fails, the other is still available. This light commercial vehicle uses a single drum brake on the rear of the gearbox as a handbrake. It's sometimes called a transmission brake. On this duo servo drum brake, the cable for the handbrake lever pulls on an actuating lever inside the brake drum assembly. The actuating lever is connected to the secondary brake shoe by a pin and to the primary shoe by a strut. Movement of the lever forces both shoes against the drum. This section examines brake fluid. The brake fluid transmits hydraulic pressure from the master cylinder to the wheels. It is a special fluid with special properties. Most are a mixture of glycerin and alcohol, called glycol, with additives to give it the characteristics that are needed. It must have the correct viscosity for hot and cold conditions. Its boiling point must be higher than the temperature reached by the system. It must not damage seals, gaskets or hoses or cause corrosion. Glycol-based fluids meet most requirements, although they do damage paint. And they absorb moisture, hence the warnings. This is important because as moisture is absorbed, it lowers the boiling point of the fluid. Brake fluid should not be mixed with mineral-based oils or solvents. If contamination is suspected, the braking system must be drained and flushed with a suitable solvent and rubber components replaced. This section examines brake linings and shoes. The drum brake uses brake shoes that have friction material called linings attached to them. This friction material was once made of asbestos, but concerns about health problems associated with asbestos have led to increasing use of non-asbestos alternatives. Linings can be riveted or more often bonded to the brake shoes. The composition of the friction material affects brake operation. Linings which provide good braking with low pedal pressures tend to lose efficiency when they get hot. This means the stopping distance will be increased. Linings which maintain a stable friction coefficient over a wide temperature range generally require higher pedal pressures to provide efficient braking. This may necessitate the use of a booster. This section examines the backing plate. All of the brake unit components, except the brake drum, are mounted on a backing plate bolted to the vehicle axle housing or suspension. The backing plate is usually pressed from heavy gauge steel. It has a raised outer edge that fits into a groove or recess in the brake drum and helps keep out any dust or dirt. Some vehicles have manual brake adjusters, so openings are usually provided to allow for adjustments without having to remove the wheel and brake drum. This section examines the wheel cylinder. The wheel cylinder is located inside the brake drum and bolted to the backing plate. It converts hydraulic pressure from the master cylinder into mechanical force that pushes the brake linings against the brake drum. Some have a double cylinder with a piston at each end. Others have a single piston with one end of the cylinder closed off. They are usually made of cast iron or aluminium alloy. Some are sleeved with stainless steel to be longer wearing and more resistant to corrosion. The wheel cylinder cups seal the cylinder against fluid loss. They operate under difficult conditions of extreme pressures and temperatures. They may be fitted with a spreader and light expansion spring to keep the lips in contact with the cylinder during retraction and while at rest. This helps keep air out of the system. Most wheel cylinders are fitted with bleed nipples to allow air to be bled from the system after assembly. A flexible cover or boot allows for piston movement and also keeps out dust and moisture.